Good morning.
Morning.
Bad news, it's Thursday. You know what that means? Friday, Saturday, and Sunday without any calculus. That's tough.
Hey, Doug, did you get rid of one of the homeworks on my open math?
What about one of the homeworks? I'm sorry.
Did you hide one of them? Because I feel like there were 5 homeworks due, and now I think there's only 4.
Yeah, a few of you emailed me because I had 8.7 due this coming Sunday, but we're not talking about 8.7 until next week. And so that was a mistake on my part. So you should just have 8.3, 8.4, and 8.5 because that's what we're talking about this week. So I just moved 8.7 to the week after that.
Okay.
Yeah, so that was a mistake on my part. Solved. Okay, let's see. Partial fractions. Yeah, okay, so we got kind of a cool shortcut today. Partial fractions is kind of a neat trick, and so let's see if we can get ourselves to understand it. Good algebra training. It's not hard. It's probably something you haven't done before. But this is kind of a neat trick that actually comes up in advanced math classes a couple of times. If you're taking differential equations this summer with me, we'll be using that for something in there. It's kind of related to this concept, oddly. And it's not hard, so let me show you how it works. Share a screen. Get some paper, put some lines on it because it seems like a good thing to do. Awesome. So let's do one more question, kind of like yesterday, and then I'm going to show you another way to do it that's ridiculously easy. So 8.5 is a trick called partial fractions. Mathematicians call it partial fractions. So let's say you are trying to integrate from yesterday's knowledge, x 9x plus 2 over x squared minus 4, and using the, let's go blue, using the trig substitution. And this is the kind of thing that would happen on a test if I didn't maybe tell you otherwise. But if you said, I'm going to use, you recognize, hey, look, Pythagorean theorem. It looks like trig substitution. So you see that it's a minus sign. And so you think to yourself that, right, that would happen if x was the hypotenuse and 2 was one of the sides. Doesn't matter which one. And so then I could choose whatever angle I wanted. And so then I kind of have 2 choices. I could either say the cosine of theta equals 2 over x, which would mean to solve for x, I'd be multiplying x up to the cosine and then dividing the cosine away. So I'd either have 2 over the cosine of x, which I like because it's cosine, or 2 times the secant of x, which I like because it doesn't have a fraction, but I don't like secant. And so that's kind of my choices, I guess you could say, as to, again, in the language of what I said yesterday, this is kind of like your converter between the 2 worlds of x and theta. And so that's our substitution. I guess I'll use secant. I don't know. I'm tempted not to use secant. Let me think about this for a second. Yeah, let's use secant. It's more painful. So if x equals secant, then that means I could proceed back up to my problem and say then, awesome, that means 9 times x, which we've now figured out is going to be 2 times the secant of theta plus 2. So the top is awesome. And the bottom is 2 secant squared which would be 4. And hopefully from yesterday, you can see why that's going to work good on the bottom, because as soon as I take 4 out, I'm going to have secant squared minus 1, and that's tangent squared. And so that got rid of that sign. But unfortunately, because there is yet a dx in this problem, we still have a little bit to go. And as we saw yesterday, this is going to get worse before it gets better. So if I take the derivative of x, I get the derivative of x. The derivative of secant is terrifyingly secant tangent. And so, whoa, that's a huge thing to have to replace dx with. This is not good. Let's see, there's a 2. I think I'll throw the 2 out front since I'm running out of room. So I get secant theta, tangent of theta. And so again, mission accomplished. Awesome. I got a new integral. It used to be black, now it's green. Sweet. But as we saw yesterday, that doesn't look good. It looks like this is not going to be good. I hope a bunch of stuff cancels out. Is kind of what you should be thinking. And so, so if I take that 4 out on the bottom and then I bring it outside, I'd have 2 over 4 out front. And let's see, what do I have on the top? I guess I'll multiply that 9 in there. So I get 18 secant of theta on the top plus 2. On the bottom, taking the 4 out, I have secant squared theta minus 1, which I notice right now is tangent squared. I'm assuming that's a good idea, but I don't really know. And then I still have the rest of that other junk, secant theta, tangent of theta. And I can see now that I have a tangent and a tangent. One of those tangents goes away. That seems like a good idea. So it's at least getting a little smaller. I see both this 18 and this 2. I could take a 2 out front, which would actually cancel that. So I don't have anything out front anymore. That's kind of nice. So let's see, I'm getting a little lost. So let's take stock of what we have. So I've got secant distributed into this statement. So I have 9 secant squared theta plus secant of theta, distributive law, over tangent. Yeah, over tangent of theta. Anybody see anything wrong with the algebra there? I'm going a little dangerously fast. So that's not so good. Like that did not clean up very nicely. I'm not very happy about that. So can I survive this question? Ay, ay, ay. And this is part of the sales pitch for today, because we're going to do this a second way in a minute using partial fractions, and we're going to answer it really fast. It's almost ridiculous how fast it's going to be answered relative to this nonsense. But again, I kind of like this because it illustrates how hard integrals really are. And so, now that I'm this far into it and I realize, wow, that isn't very simple, I think to myself as a teacher, boy, I got to make sure I don't give them that question on the test. I sure hope the book didn't give him that question. Like, this is a tough one. This is a mess. But this is good practice for us. So let's keep on going just to see if we can actually survive it.
Hey, Doug, doesn't this look good because the derivative of tangent is secant squared?
Yeah, frankly, if this over here wasn't there, then I'd let u be tangent, and the derivative of tangent is secant squared, and that'd be terrific. So good observation. Now, having said that, to your point, Connor, would you agree that since there's a plus sign there, I can actually break this into 2 separate problems?
Yeah, I just was wondering because you're saying it looks so ominous. I'm like, I feel like it should look good.
Good for you. That shows some strength of mind on your part to be able to see kind of past that. So do you realize that this is actually kind of 2 separate problems now?
I didn't realize that right off the gate. So part of it was blissful ignorance.
Yeah, but I like that you're thinking substitution. The fact that you're getting the sense of substitution. So your intuition is starting to grow. So good for you. So yeah, for this first one over here, I don't think it's actually going to be that hard. So let's try that. So for this one, if we let u be equal to the tangent of theta, then that would mean du equals the secant squared of theta d theta. So then this problem would become, I have 9 times secant squared on top. I have tangent of theta, which I'm now choosing to replace with u, and then I've got to replace d theta, which would be du over secant squared theta. And so you're exactly right. But it's very important to understand that you had to switch these. That plus sign was very debilitating. The fact that I was able to break this into 2 is what made this possible. So, okay, this is great. So that means that's the integral of 9 times 1 over u. Hey, that's natural log. So this would be 9 natural log of u. Technically, and I usually don't worry too much about technicalities, but that would actually have to be an absolute value, even though I really don't tend to write that in there. Occasionally that'll come up to bite you, but I don't have any examples in my mind when I say that. Let's see. And so we said actually then u was actually the tangent of theta. But remember, there wasn't even a theta in this problem. And so let's go back to the right triangle up here. Tangent of theta. Can't I figure out what the tangent of theta is from this? Except for I need the opposite over there. So Pythagorean theorem would tell us that that's x squared minus 4. So the tangent of theta would be square root of x squared minus 4 over 2. So it just got a little uglier. So there's actually part of our integral. It's actually done now, as horrifyingly ugly as that is. So what about this other part over here? I don't have the same luck. Is that easy? Is that hard?
Wouldn't that one turn out to be 1 over secant square or secant, which is equivalent to cosine?
Yeah, let's play with that a little bit. So let's see. Secant is 1 over cosine, and the tangent is sine over cosine. So that would be 1 over cosine times the reciprocal, cosine over sine. So the cosines cancel. So it's 1 over sine, which is cosecant. So this is actually the integral of cosecant. Which is very similar to the integral of secant, which we made once. And remember, that was that terrifying substitution. In the interest of time, rather than trying to do this from scratch, I'm going to look at our book, the table.
No, I'm saying if you let tangent equal to u, you'll get secant square underneath. And then won't you be able to cancel out the secant on top and have 1 secant underneath?
Yes, but then you'd have, if I'm thinking about what you're saying, right, you'd have 1 over u, but then you'd still have a secant down there.
I forgot the u. I'm excluding the u in my equation.
And so, yeah, that's not impossible, but it feels ugly, it feels messy. Good thought. I like that. There is more than one way to do these, and that's kind of the point of today, is that in the end, sometimes you choose the hard way and sometimes you choose the easy way. But I'm looking it up. This is number 8 in the back of your book. It says, oh my God, this is terrifying. The integral of cosecant of theta is actually equal to negative natural log, absolute value technically, of cosecant plus cotangent. Do you vaguely remember that secant was like that too? Secant and cosecant are kind of brothers, if you will. And so secant was weird too. And I showed you once the crazy substitution. So the integral of secant was natural log of secant plus tangent. The integral of cosecant is natural log of cosecant plus cotangent. But again, there was no thetas in this. And so I've got to resort to this right triangle, which I think I'll make a copy of so that we can be looking at it simultaneously. Copy, paste. Put you right there. So cosecant, oh man, trig is so painful. Trig. Cosecant, let's see. This is how I think about it. I don't know what cosecant is, what two sides, but I know that cosecant is the reciprocal or the flip of sine, and sine is opposite over hypotenuse. So cosecant would be hypotenuse over opposite then. So that's x over square root of x squared minus 4. And cotangent is the opposite of tangent. So instead of being square root over 2, it's 2 over square root.
I have a
Boom.
question.
Sorry?
For the original integral, can't we just split it up using the plus sign, like do the integral of 9x over x squared minus 2 over 4?
Yeah, that's exactly right. Couldn't we have, just like we split this red integral right here into two parts? Couldn't we do, this is an option, and couldn't we have done that at the start? In other words, I'm going to erase this, but couldn't I have said this is the integral of 9x over x squared minus 4 plus the integral of 2 over x squared minus 4? Like, might that have been easier? The answer is, yeah, that might have been easier. That might have saved us some trouble. Maybe it wouldn't have, I don't know, but that's an option for sure. And that's why I think this problem is worth the trouble, that you just see that, you know, real integrals, when you just make up a problem, which is what I did here, are kind of terrible. And so in a sense, you don't want me making up the problem unless I test it out myself. This problem is horrible. I mean, it's just gigantic. The fact that we think we just got the answer to this, I almost find myself wanting to just write it all down, and I can't even believe that it's even right. So then we're saying there's the original problem, and we're saying there we go. There's the answer. Now I will write it a little simpler. Watch this, just a couple simple simplifications, but we're saying, I guess that's, well, I can't see anything to do with this first one. 9 natural log of square root of x squared minus 4 over 2. Notice these two fractions have a common denominator already, so I might as well add them together. Does that make sense? Of x plus 2 just over 1. Technically plus c. So, you know, if I haven't made an algebra mistake, which I don't know about you, but I feel like I probably did. Like there's a lot of steps there. Like I have to be really careful, and wow, that's insane that that's the answer to that statement, you know, supposedly. So I just found myself going, wow. Whew, that's horrible, ridiculous. Now let's try this, not using such a ridiculous technique. Let's see, how do I get? Now let's try this using a ridiculously brilliant idea on the part of some nerd. Let's see, I called that trig substitution. Now let's call this partial fractions. Let's try this again, but with partial fractions. And I think I'm going to move this down a ways. Let's go all the way down to here. And this is related to what April just said, except it's even better. Let's try partial fractions as a technique. Partial fractions is this. It's where you look at that fraction and you think to yourself, hey, is that possible to rewrite that fraction before it was added together? In other words, you see this as a fraction that's been added together. So let's just consider our fraction here for a statement. Would you agree that 9x plus 2 over x squared minus 4, the bottom number, if you will, is composite. In other words, it factors to x minus 2 times x plus 2. So the question is, if we unadd this fraction, hey, look, there's two different denominators there. So the question is there some way I could unadd it as though it used to be this, some number over x plus 2 plus some number over x minus 2? Do you see that usually you go this way? You add fractions by making a common denominator and then you add them together and you get an answer. The fact that that bottom number is factorable, if we could split it up like April suggested, but even further separated in the way that I'm showing you here, this would get really easy. Because remember what made these problems hard was that dumb squared right there. That's what brought all this trig nonsense for the whole entire week into play, because there was a squared there. If it wasn't for that squared, we wouldn't have had this problem. And so if we're able to actually split this up going this direction, then because of that plus sign, I'm going to have two separate integrals, and this problem is going to be really easy. So how would that work? Well, if this is going to be true, then to get a common denominator, don't you have to multiply this one top and bottom by x plus 2? Hey, look, they have a common denominator. And this one over here, top and bottom by x minus 2. Isn't that what it takes to add fractions? There, look, they have a common denominator. Now I can add them. So I can say that if I distribute this in here, I can say that ax plus 2a plus bx minus 2b is over the top of our denominator. And so if I can somehow choose an a and a b that make those two statements equal, if I can find an a and a b that make both of those statements true, then I'd be in really good shape. Does it make sense then to you logically, working backwards, that ax plus bx, so wouldn't a plus b have to be the 9 then? Do you agree with that? Ax plus bx, those are your x terms, and don't those have to add up to 9? So a and b could be 7 and 2. 7x plus 2x is 9x. It could be 5 and 4. 5x plus 4x is 9x, right?
Can't you just solve that equation for b or a and then plug it into the other equation? So that way you have one variable and then you can solve for the one variable and then plug it back into the previous. Do you know what I'm saying?
Yeah, yeah. There's a number of ways this could be done. I think this is the easiest to see maybe, but no, there's lots of ways to do this. And then our constant of 2 up here in the top equation, our constant of 2 is going to have to come from the two constants down here, which would be 2a, positive 2a, and negative 2b. So there's two equations, two unknowns, the backbone of linear equations. You have a system of two equations and two unknowns to solve. This is one way to do it. So let's see, this looks easy to solve to me if I multiplied this one by 2, because then it would be 2a plus 2b plus 8, equals 18. And the bottom one would still be 2a minus 2b equals 2. And then if I added these two equations together, the b's would cancel out. That's why I multiplied the top one by 2. Is that ringing a bell from your previous math knowledge? Oh, look, somebody was nice to us and made this problem to come out with whole numbers. So if a is 5, and then I go look back at either one of these two equations, if a is 5, then b would have to be 4. Let's make sure that works down here too. Is 2 times 5 minus 2 times 4 really equal to 2? Look at that, 10 minus 8, yeah it is. So that means I just did something that's going to make my life ridiculously easy, because now I can say that the integral of 9x plus 2 over x squared minus 4 could be thought of as the integral of a over x minus 2, but we just found out a was 5. And separately, because we love plus signs, b over x plus 2, but b was 4. So we never had to change letters. Do you see those as really easy problems now because we effectively got rid of the squared? Because that's not squared, the derivative of x is just 1. You can use substitution if you want to. You can say u is x minus 2, but because that's just x, not x squared, you don't really have to substitute u for that. If you can. But all you're really going to get for this is 5 natural log of x minus 2, because doesn't the 5 just come along for the ride? It's the integral of 1 over junk. That's the natural log of the junk, as long as there's no derivative. Remember, this works because the derivative of x is just 1. If it had been x squared, this doesn't work because there's more to it. Plus 4 times the natural log of x plus 2. I'm done. Bam. This is what mathematicians do. They just look around for, tricks and ways, like, how can I solve this problem? And maybe this isn't solvable. And so now, does that answer bother you at all? Should. Why should that answer bother you?
It's not the same as our other answer, is it?
It's not even close to the same as our other answer. Look how nasty that other answer was. So are those the same, but they don't look like it? Or is one of them right, one of them wrong? So let's just play with this for a second. See if you still know your logarithm properties, because it turns out they're actually the same answer, but the green one there is just horribly ugly. Do you remember the property of what happens when you have, and these are things we ran across from time to time, but people tend not to keep these in their head very well. Do you remember what happens when you have the natural log of a number divided by a number? How can you rewrite that? Because that's what we have here, right? Something divided by something.
I think they subtract.
You're exactly right. Good memory. That's the same as subtracting them. And that's because logarithms are exponents. And just like with exponents, when you have like x to the 7th over x to the 3rd, can't you subtract those exponents? So division is related to subtraction. So that's why that works. So that means I could take this green equation here then and write it like this. I have 9 times the natural log of, and I'm going to write it this way, the square root of x squared minus 4. And you also are multiplying by 9, so I think I'll multiply the 9 in there. 9 natural log of 2. Do you understand why there's 9 in both places? Because if it's a subtraction problem, there was a 9 out front here, wouldn't both of these get the 9? Because you have to distribute it. And then wouldn't the other one be, notice it's a minus, you got to be careful here, minus the natural log. Actually, I think I'll write it a little more carefully. The natural log of x plus 2 minus the natural log of the square root of x squared minus 4. But then who can tell me about this? This has come up, we've talked about this, but if you have the natural log of, say, x squared, what's true about that 2? It's the natural log of something to a power.
Can't you multiply it in front?
That's exactly right. That job, Eve. That 2 can come down front. And that's because there's a relationship between multiplication and exponents. In other words, if you add x to the 2nd to the 3rd, don't you multiply those? In other words, the fact that it's raised to the 3rd implies multiplication. Hey, look, our x was raised to the 2nd, it implies multiplication. So It's logarithms are exponents, so that's why that's true. And that's also why I wrote this with 1/2 there. So that means this 1/2 can actually come down front. So you have 9/2 natural log of x squared minus 4. You have minus 9 natural log of 2. You have minus natural log of x plus 2. And then notice it's minus a minus, so that actually becomes a plus. And the 1/2 comes down front, so it's plus 1/2 natural log of x squared minus 4. Can I do anything with that?
You can add it to the 9/2.
Yeah. That's exactly right. In other words, these two terms are exactly the same term, aren't they? So if you have 9/2 of that plus 1/2 of that, isn't that 10/2 or 5? So you have actually 5 natural log of x squared minus 4. And you have minus the natural log of x plus 2, and you have minus 9 natural log of 2. Hey, this is starting to look kind of like our other answer. As a matter of fact, it would look exactly like the other answer, except for there's a 4 right there.
Also, in that answer, we don't have x squared. It's just x.
Well, that's right. That's x squared, isn't it? So, what's that? Oh, let's think about this a little bit. Isn't this 5 times the natural log of, hey, doesn't that factor to x minus 2 times x plus 2? And aren't those multiplied? And so according to the same property we talked about above, if you have natural log of junk times junk, isn't that the natural log of junk plus the natural log of junk? Isn't that true? Minus the natural log of x plus 2 minus 9 natural log of 2. Hey, look, these are the same. Now what's my answer? 5 natural log of x minus 2. If I have 5 of these highlighted minus 1 of them, don't I have 4 of them? Whoa. Whoa. That's exactly, well, it's not quite exactly the same. What's different?
There's an x minus 2 in the 5 times natural log. And we have an, oh wait, never mind. That's wrong. It's the 9 natural log of 2.
Yeah. Did you notice they're exactly the same except for this? The answer is we didn't do anything wrong here. Do you understand why?
Wouldn't
It's
that
just-
be implied as the C?
Exactly
Yeah.
right. Plus a constant. So that's why the plus C is kind of important. So even though those two answers kind of look like something's different and like we made an algebra mistake, they're not. And I actually kind of went back and erased this earlier, but when we got this answer, remember there was a plus C there? Technically there's a plus C. In other words, those two answers are the same. They only differ by a constant. Well, you can have any constant there you want. And so 9 natural log of 2 is a constant. So oddly enough, they actually are the same. But of course, this first technique here that we used was utterly horrifying. I mean, that's just that's the worst integral. Oh my gosh, that's just terrible. And on top of it, we had to be amazing at natural logarithm properties to kind of simplify that down. Because remember, the point of an integral is to come up with some expression that you can plug numbers into and find the area under a curve. So this second technique was uber simple, and it produced a simple answer with relatively little work. Now, again, I think this is just kind of neat to see and so forth, but we're pretty far out in the weeds here. You know, do we really in the real world, do we need to be this good at natural or at integrals? Well, maybe if you want to go on to advanced math, occasionally this kind of thing will come up, but not very often. I mean, we're pretty far out there. So fine, but again, I hope, and you notice like the assignment questions in 8.5, they're designed and they're given to you so that you would do them by partial fractions. And so that'll be the technique to use in this section. But again, I caution you because if a year goes by, or, if I was mean on the final exam, I could just give you random problems and say, get the answer right. And you have all these techniques and it could take forever to answer them, right? So good thing that you're told that. So on a test, if I want you to use partial fractions, I'll probably say use partial fractions to take this integral. Let's try that right now. Now, this is also kind of a different question, so I want you to stare at this and kind of see if you see why. What if I asked you to take the integral of this? Notice how there's a plus 2x there. We've never had that before. We've only had that on the bottom. And we said, hey, that looks like Pythagorean theorem, right? And so we were able to make a trig substitution for it. But does it make sense with that there? That screws up that option. Can you see that really, thanks to that 2, trig sub won't work? Can you see that? You see the logic in that? Not sure how well you're tracking with this conceptually, just seeing it once. So,
But instead of having a rectangle now, don't we have a parabola, which we factored a lot in, I think, Math 111?
yeah, so we're not intimidated by parabolas, but I'm not going to be able to draw a right triangle of this because of that 2x. That's kind of the idea here. And so,
Yeah, totally not intimidated by parabolas at all.
by the way, like we won't go down this road, but would it work to just let u equal x squared plus 2x minus 15? What's the derivative of that? Two x plus 2. Well, if there had been a 2x plus 2 up here, it would have worked, but there's not.
Would you run that denominator through the quadratic formula?
That's an awesome idea. Could you throw that in the quadratic formula? And really what you're asking there as an idea is a good one. And it really has to do with completing the square. So I'll show you that really quick. Would you agree that if this was x squared plus 2x plus 1 minus 16, do you agree that's still minus 15? Why did I write it that way? Because now this part of it could be factored to x plus 1 and x plus 1. And now it does kind of look like the Pythagorean theorem. Does that make sense? So you actually could mess with this and get it to look like Pythagorean theorem, and you could actually still do this problem with the trig substitution. However, it is horrendous, just like the previous problem was. If you separate this with partial fractions, if you recognize that denominator down there is actually factorable, it's going to be a way easier method. So, so you need to be told that. You need to be told which method to use. And so that's pretty astute of you, Jaleesa, to notice that. In a sense, the quadratic formula is helping you factor it. That's kind of what it comes down to. But completing the square is also an option. So what we're saying then is there some way to unadd this, to decompose this fraction is kind of the way you might hear it sometimes. We're going to decompose this fraction. Well, this problem is canned in that it was made up to factor nicely. If I just make up random numbers, that's not going to happen. But this factors to x plus 5 and x minus 3. So it's nice, clean answers. So the question becomes, is there two fractions that I could have had before adding them together? If I could split this up in that way, that would suddenly make this problem really easy. And so I do what I did a second ago. If I take a over x plus 5. In order to find a common denominator, I'd have to multiply top and bottom by x minus 3. And for b, which is presently over x minus 3, it would need an x minus 5 top and bottom for a common denominator. And so the question is, if I multiplied this out, if I have a times x.
Wait,
and
isn't that supposed to be x
b
plus 5?
plus 5. Thank you for fixing my stupidity. And I added bx plus, thank you, Eve, 5b. Then I would need that to be equal to 11x plus 23. Now I showed you a technique for solving this. What was your idea, Eve? You had some other idea about how we should solve this. What was your idea?
I said that you could take the first equation, like I think it was x plus b equals a number. I was gonna say you could solve it for like a, and then plug it back in for b. That solved equation for a for b. Wait, I'm really bad at explaining this. I know what it is, but I'm bad at explaining it. So you solve your first equation
When you say
for one of
first,
the
you mean-
unknowns, and then you
you
plug it in for that unknown, so you have the same same variable.
Yeah, I'm having this recollection that there is another way to do this, and I can't remember what it is. And so I'm wondering if you're hitting on it. And that's so when you say solve your first equation, you mean which one? Up here, this one, or maybe you haven't fully formulated your hypothesis, your idea yet.
If you go back to the other equation, I think I could do it because I'm having a problem realizing it. Here, I'll try it on a piece of scratch paper and I'll let you know.
Play with it for a second. I'll show you something else that's kind of cool. I think we've had some occasion to do this, but again, do you agree that ax plus bx will have to take care of 11x? That's the only way I'm going to get it. So a plus b has to be 11. And again, if somebody's nice, then the a and b are 8 and 3, 6 and 5, 4 and 7, something like that. And then the constants also have to work. So minus 3a and 5b are the constants. And so that's going to have to add up to 23. So there's my second equation. Minus 3a plus 5b equals 23. So let's solve this using the matrix feature of the calculator. I'm confused because I teach so many different classes. Have I already showed you this? Do you already know this? I'm going to share a screen.
I've done it in my engineering class, but I don't know if we've done it in this class.
Yeah, that's I'm thinking I've been doing it recently, but I'm thinking it was with my engineering class. So
I remember being showed the matrix feature in this class.
I've shown it to you in here. Okay, good.
I think so. I mean, I don't know.
So let's do this. So if you say second matrix, and by the way, spring term is coming, Math 261. I think maybe I've given you the speech before, but Math 261 is linear algebra, which is kind of the background. I'm about to show you buttons to push, and maybe I'm reviewing this. But Math 261 is the theory behind how this all works. So what I need is, because I have a matrix, I have two equations, but there's three columns, an A column, a B column, and an equal sign column. I need to edit a matrix, and I need it to be 2 by 3. And when I do that, notice it gives me a spot to enter all 6 of those numbers we just had. We had AX, in other words, 1A, plus BX, in other words, 1B, has to equal 11. So does it make sense that first row? The first column is A, the second column over is B, and the third column over is the equal sign. And when I get to the second one, it was negative 3A. And then it was positive 5B, and then it was 23. And so the calculator will do this for us. Now this is more trouble, like what I did a minute ago. This is way more trouble to go get your calculator and answer this. But when you get to 3 equations, 3 unknowns, which is something we'll do in differential equations in this summer, there's occasionally reasons to do this where you got to break it into 3 equations. 3 equations, 3 unknowns is much better to use the matrix. So awesome. Everything is in there. I say second quit. I go second matrix again, except for this time I'm going to do math to that matrix. And the math that I want to do is all the way down here called reduced row echelon form. RREF, reduced row echelon form. And it's waiting for me to say what matrix I would like to do that to. So I'll go second matrix. And then I just arrow myself to A. And bam, there it is. So notice if you reread this, wasn't the first column A, the second column B, and the third column the numbers? So this first equation now reads 1A plus no B equals negative 2.25. Oh, A is negative 2.25. And B is 3.25. So that's what reduced row echelon form accomplishes. So I'm going to write that.
Hey, Doug, before we go on the equation any further, I think you might have wrote 1 instead of 11 on your matrix.
I was actually surprised that came out as decimals. And so let's go check and see. Let's go edit this matrix and see. Bam. Thank you for rescuing me yet again. That was 11. I think I clicked it twice, but I don't think it showed up. I
got 4 for A based on my method. I don't know if that's right or not.
Oh, good. So you think you figured your method out? I made these problems up and I made them to come out as whole numbers. And by the way, you might think for a second, you future math teachers, how did I make that up to come out as whole numbers? Reduced row echelon form. Uh-oh. I've screwed this all up. Clear. 2, 1 is negative 3. Enter. Second quit. Second matrix. Is your idea better, Eve, in terms of being fast?
Depends on how good you are at algebra.
That's a good answer. I like that. Yeah, so it should be 4 and 7.
That's what I got.
Woo! A equals 4, B equals 7. So let's quickly finish this because we're sort of home free now. Again, do you agree that was don't go do this with the matrix. If it's 2 equations, 2 unknowns, just use your basic solving techniques that you learned before. So that spent way more time than we did just doing it by hand the first time. So that's just good to think about. But it's also good to have lots of tricks up your sleeve, lots of methods. It's the same thing I'm teaching you about integrals right now. We've got all kinds of ways to do things. So all of this to say, I can stare at my original problem and decide I am terrified of it and that I do not know what to do. But we just figured out that that's the same thing as A over x plus 5, but A is now 4. And I can do this as 2 separate problems then. Plus B, which is 7 over x minus 3. I left out the dx's because I don't have room. So, hey, that's a way easier problem. Is everybody okay with the fact that I'm ignoring this? Just a side note, but if I said, what's the integral of 1 over x squared? It is not the natural log of x squared. Do you understand that? It seems like it would be, but take the derivative of natural log of x squared. Isn't the derivative of natural log of x squared 1 over x squared? But because that derivative of the x squared is not nothing, I have to say times the derivative of x squared, which is 2x. And I end up getting 2 over x. That doesn't work. I didn't get the right answer. Because of the chain rule. Well, because this is only an x minus 5, isn't the derivative of x minus 5 just 1? That's why it works. So I don't have to replace x plus 5 with u or something like that. I can just say I'm done. It's 4. Since that term down there is linear, meaning it's just an x, I can say there's the 4 comes along for the ride. Remember, you can pull the 4 out front, so there's really just a 1 there. And so I'm done. And technically there'd be a plus c. Cool. We'll let you decide this, Eve. Is your technique cool enough that it's worth, in your opinion, is it worth us looking at as a method? Is it sort of
I don't know how
staying
worth it
with
it
the
is. Like
easier-
it's mostly algebra, but it might be good for the brain. I don't know.
Yeah, it's a tough call. Let's do it real quick. This isn't a hard method, so let's at least talk about it. Maybe we won't do it completely, but
Okay, so what I did is you might want to move your 2a plus b equals 11 and minus 3a plus b equals 23. You might want to move that down so you can kind of look at that because that's the two equations I used.
so you got it to here and then you worked with that from there?
Yep.
Got it. Okay, so let's do that. Okay, I think I see where you're going with this then. So there's more than one way to solve two equations, two unknowns. Go ahead. What did you do then?
So I solved the first equation for b. So I said b equals 11 minus a, not 5a. And then I plugged that solution for b into the next equation. So I said negative 3a equals 5 times 11 minus a. And then I solved for a.
Yeah, so substitution is another technique for this in the sense that I have two equations, two unknowns there in pink, and I got to get one equation, one unknown. My method by hand earlier was to add them together to make one of them go away. And this method, substitution, also accomplishes it. So notice by putting what the top equation is, I hope this is a review. The top equation solved for b and replacing it down below, don't you get one equation with one unknown? And so now you can proceed negative 3a plus 55 minus 5a. Oops. Minus 5a equals 23. If I add the a's together, I get negative 8a. If I subtract 55 to the other side, I get negative 32. Oh, look at that. A is 4 again. Still got the same answer. So yeah, substitution is another way to solve two equations, two unknowns. So two equations, two unknowns, you're actually better off to do by hand because it's just faster. But three equations, three unknowns, the matrix is kind of cool. Or from there, four equations, four unknowns. And that's what 261 introduces, is what's called linear algebra. Because aren't those two pink equations both lines? Notice there's no squareds there. It's not a squared, it's not b squared. So linear algebra is saying, well, what if there wasn't just an a and a b, but what if there's an a and a b and a c? And so, what's reduced to echelon form and how does that work? And it's kind of trying to automate that process a little bit. How can you automatically or faster solve lots of equations, lots of unknowns?
So real quick, when I initially factored that parabola under the original integral, I wrote mine as x minus 3 times x plus 5.
Yeah.
So I had my a over x minus 3.
Yeah.
So I had 4 ln of x minus 3 plus 7 ln of x plus 5. And when I put that into Desmos, mine gives a different answer than yours.
Yeah. So either I or you made an algebra mistake in the sense that it doesn't matter which one you put over which one. If I had switched these, if I'd called this B and this A, then I would have got the same answer as 4 and 7, but they would have been backwards. Like if A was 7, now B will be 7. Like you should get the same answer in the end. It doesn't make any difference.
Okay, yeah, I'll look at mine to make sure I didn't do something dumb in here.
Yeah, well, you watch me do a couple things dumb, so it could be mine just as well as it could be yours. But you should get the same answer. Everybody understand what she said? Because there's a choice there, right? Like she's basically just saying she happened to write these two statements in reverse, and therefore this statement had the x minus 3 and this statement had the x plus 5. It's the same exact thing, but you should get the same answer and it won't make any difference if everything goes well. I don't think I'm going to do this one for you, but I'm going to give you time to do it yourself, and let's see what you get. I also want to take a quick look at your assignment while you're doing that and see, because there's some harder questions you can give in this section, and I want to see if I assigned any of those. I hope I didn't, because when you see kind of a genuine parabola sitting down there, that's kind of a key. Like if I didn't give you any help, that's kind of a key that this problem is not going to be able to be done by trig substitution. So again, this problem is canned. I made this up. So it should come out pretty nice, pretty quick. See if you can pull that off. Does everybody get that written down? Because I think I'm screwing up your screen now. Everybody got it? 7x minus 36 over x squared minus 6x minus 16. Oh yeah, they do take this to another level. Perfect.
So I assume since we've got a minus sign between the two terms at the top, that would be a minus sign between our fractions, right? Once we get it factored and solved for A and B.
That's right. So you'd have natural log of one thing minus natural log of another thing. That's exactly right. If that comes up here. I'm going to quickly catch up to you since I'm probably faster at this than you are. Which probably means I'll make another mistake, but
So Doug, that's kind of where I got stuck. How do you know that A plus B equals 7?
because you have AX plus BX, those are the only X terms.
Oh, okay. Thank you.
Good question.
Where did that 2A come from?
Because I was skipping some steps up here because I was thinking of it as A over X minus 8 plus B over X plus 2. So when I multiplied this one top and bottom by X plus 2 and this one top and bottom by X minus 8, I have A times X and A times 2.
Okay.
That's wrong. Let's see, 8. So if you didn't blow the algebra, you should have got to the integrals that I have set up down there now. And there isn't a minus sign.
Oh, you better believe I blew the algebra.
Good, I don't want to be alone.
Yeah, I think I got mixed up when I was multiplying the terms out. I might have gotten that part wrong. So I was confused by the 2A.
I think that is the actual retail value of the showcase.
So why is it A plus B and not A minus B?
Well, you can make, if you chose to, you could go back here and say, I think I'm going to try to find two fractions that subtract to give me 7x minus 36, but adding is easier than subtracting. So I'm just picking plus. Now, if A or B happen to come out negative, then fine, then it's a subtraction problem. Like if B came out -5, then it would have been, oh, 2 over x minus 8 minus 5 over x plus 2. So like one of those could come out negative, but making two fractions add is much easier than subtracting.
I think I've just been carrying this negative sign around arbitrarily because it was 7x minus 36.
Yeah, the only place that negative sign lands is is just over here at the end. In other words, my two fractions added together are going to have to equal that denominator or that numerator.
Hey Doug, could
Yeah.
you possibly show how you found A and B? Because I'm still stuck on that part.
Yeah, so in this case, I like what mathematicians call elimination as a method. So what I did is I said, hey, look, there's a b and a negative 8b. So if I took this equation up here and I multiplied it by 8, then that top equation would be 8a plus 8b equals 56. 8a plus 8b equals 56. And now I can eliminate one of the variables by taking these two equations and adding them. 2a plus 8a is 10a. Negative 8b plus 8b is no b's. Good, they're gone. I got rid of a variable. Negative 36 and 56 is 20. Oh, okay, so a must be 2. That's what I did.
I don't know what for some reason I put negative 5b. That's why I was stuck on it.
Screwed up. Yeah, well, you watch me do that, so.
And then when you're writing your answer, do you have to be careful to like keep the x plus 2 or x minus 8 with the a or b? Like it's arbitrary which one you assign them to, but you have to keep them at the end.
No, it's not arbitrary because in my case, the 2 went with the x minus 8. So I've got the 2 with the x minus 8 down here.
Yeah, okay.
Yeah. All right, we got to do one more example and then we'll be done. I was hoping that I did not throw you these curveballs in the assignment, but it looks like I did. So what about this statement? This doesn't look at the outset terribly different, but it turns out to be different. I just made this up, so I hope I didn't screw up the algebra that I did in way too quickly here because I want it to come out nice.
The x cubed makes me uncomfortable.
You're very quotable, Eve. Yeah, that's not good, is it? So what if the top is nastier? Like what if there's a bunch more junk? Well, it turns out that actually isn't terrible. So your discomfort was not going to last long. I have good news, Eve. So there's two things about this problem that are nasty. One of them is the fact that we got all this other junk up there, right? Like we're okay with that, but what's all this other junk of what you speak? Well, that's actually not terrible. So watch this. If you do what that says to do, notice it's junk divided by junk. In a sense, this is what mathematicians would call an improper fraction. In other words, it's kind of like saying, hey, I got 9/4. I got a number bigger on the top than the bottom. I got cubed on the top and I've only got squared on the bottom. And so I'm uncomfortable with that. Correct, Eve. But can't you either by synthetic division, which is hard, or just good old fashioned long division, couldn't you actually simplify this a little bit. Here's the moment of truth as to whether I multiplied this out right. Because this should go in evenly if I didn't choke. And so can you still do this? Let's see, x squared times what gives you 2x cubed? I see I need a 2 and I need another x. You agree with that? X squared times 2x. Yeah, that's 2x cubed. Good. But then there's also 2x times 4x, which is negative 8x squared. And then there's also 2x times 4, which is 8x. And very important, aren't you subtracting these in long division? Lots of you guys grew up using calculators really early, so whether or not you're still good at long division is in question, I think. But you subtract everything. So 2x cubed minus 2x cubed is gone. Negative 3x minus a negative 8x, that's actually negative 3x plus 8x, which is actually 5x, or 5x squared in this case. And then negative 6x minus 8x is negative 14x. And then I bring down that next term and I just start over. X squared times what gives me 5x squared? 5. But then I have to keep going and multiply everything out. So 5 times x squared is 5x squared. 5 times negative 4x is negative 20x. And 5 times 4 is 20. And again, I am subtracting those. So the x squareds are gone. Negative 14x minus a negative 20x is negative 14x plus 20x, which is 6x. And then 1 minus 20 is negative 19. What does this mean? What do I do with this remainder? I mean, if you take 9 divided by 4 and you get 2 remainder 1, what do you do with that? What does that mean? What's the 1?
2 1/4.
Yeah, you put that 1 over the denominator. So you don't say remainder, you just say it's 2 1/4. Well, I'm going to do the same thing here. So in other words, our problem just became the integral of 2x plus 5 plus our remainder, which was 6x minus 19 over our denominator. That's our new problem. Now
You said this was going to look better. It only
does.
looks worse to me.
It does. Check this out. Isn't this the integral of 2x? It's its own problem. Plus the integral of 5, that's its own problem. Plus the integral of 6x minus 19 over x squared minus 4x plus 4. Easy. The integral of 2x is x squared. The integral of 5 is 5x. Like, problem solved. Now I'm sort of on my home turf. I can handle this problem. So is it a pain? Mm-hmm.
Yeah, I didn't think I'd be seeing the polynomial division after Math 96 or whatever it was when they introduced it.
Yeah, you see it in Math 111 and you spend quite a bit of time on it there, but it feels very forlorn. But again, don't forget, we are way in the middle of the universe here. Like, what idiot ever wants to know the answer to that question, right? And keep in mind, I hurriedly just made this problem up, which means there is no human on earth that knows the answer to this integral. Isn't that weird to think about? I just made that up, and there's no way any person has made up that exact same integral. So we're about to know an answer that no person in the universe knows. So the only defense of this is, well, I guess that's something. But something's going to happen here. So watch me do this. Something's going to happen here that is not good. So we're done. We got these two things solved, but we still have this integral of 6x minus 19 over factored. Hey, that's interesting. X minus 2. It factors to the same thing twice. Do you notice that? Is that a problem? Well, let's find out. So that means I would need a over x minus 2 plus b over x minus 2 to be equal to 6x minus 19 over x minus 2 squared, apparently. Well, notice they already have a common denominator. Isn't that weird? Is that going to work? Well, they already have a common denominator, so there's no reason to multiply them by anything. So now it just means I need the two constants a plus b to equal 6x minus 19. Why is that not going to work? Well, how are you going to get an x term if there's no x's? Does that make sense? I can get a plus b to add up to negative 19 in lots of different ways, but there's no x terms, and so you have no way to get an x. And so it turns out to be a special case. Like if you end up with the same, if it factors to the same exact thing twice, then you've got to be a little more trickier about this. What do you have to do instead? Well, here's one way out of it. In the interest of time, we don't have time to reason about this too much. Don't go x minus 2, go x minus 2 squared. Okay, let's try that. Can we get that to be equal to 6x minus 19 over x minus 2 times x minus 2? Well, notice this one, the a, doesn't have all of the x minus 2's the other one does. And so if I multiply this one top and bottom by x minus 2, does it make sense they now have a common denominator? And so then I'd have a times x and a times 2 when I distribute a in there, and then plus b, and that would have to be equal to 6x minus 19. Well, that's a cool trick. Now I have an x term. But I only have one of them. So apparently a is 6. I don't have a choice. The only way ax is going to be 6x is if a is 6. So if that's true, then what about the constant? Well, negative 2 times a, which we just figured out was 6, plus b has to be negative 19. So that'd be negative 12. So if I add 12 to this side, then that would leave b to be negative 7. Wow, I didn't screw up that algebra. That's amazing. Okay, so wait a second. You say I'm lost. Let's go back to what we were trying to do here. We were trying to figure out what the answer to this question was. And we just figured out a way to split it up. If a is 6, and remember that was over x minus 2, and b is negative 7, and that was over x minus 2 squared, that would do it. So then I have the integral of 6 over x minus 2, which is easy. We know that. It's done. We're done. It's 6 times the natural log of x minus 2. Bam, another answer. But what about the integral of 7 over x minus 2 squared? How are we gonna, is that terrible is that a hard integral to take? Because it's squared, I wish I could tell you the answer is, wish I could just say it's that, but it's not.
it's like the x squared equation where it like gets completely different, you know?
That's exactly right. The integral of 1 over x is the natural log of x, but is the integral of 1 over x squared natural log of x squared? No, it's the integral of x to the -2. And you can just do power rule. Add 1 to that. Add 1 to that. So it becomes x to the -1 and then divide by -1. So I guess that would be -1 divided by x if I wanted to move that to the bottom so it didn't look so weird. So it's actually -1 over x. So you don't need natural log for this because it's squared. Let's go a little slower. So let's go a little slower here. So I'm going to let u be equal to x minus 2. Well, notice that's cool because du equals dx. And so I can think of this problem as, oh, the -7 comes out front. And now I just have 1 over u squared du. So that's really -7 to the integral of u to the -2. And as we said a second ago, you add 1 to that, which makes it u to the -1, and then you divide by that variable or that exponent, which would be -1. So you have -7 over -1, and you can put the u down on the bottom as a +1, and then look, those two negatives cancel, so you just get 7 over u. But remember, u was x minus 2. So the answer to that is 7 over x minus 2. So it did not invoke a natural logarithm. Woo! My brain's in pain, you say. I get that. Let's go back to this original statement and at least write out what we have for an answer, because we did so much work here that I can't even remember all the problems. So copy, paste. So we are saying then that the integral of that statement dx was, well, what were our answers? Going back up here to get them. There's the easy ones, x squared plus 5x. From the whole numbers. And then we had this one right here, 6 natural log of x minus 2. And then we had that last answer that we just got to tack on to the end, which is plus 7 over x minus 2, technically plus c. So we're saying that is the answer to this ridiculous integral. So because we were running out of time, I introduced 2 problems at once. In other words, what happens if that numerator is cubed and the denominator is only squared? And of course, it could go from here, like the top could be to the 7th and the bottom could be cubed. And, you know, it's like we could even get further out in the universe. But the point is if your power on the top is 3 and your power on the bottom is 2, like you got to do some division and get it down to a little simpler. And if you pull that off, the whole numbers that come out of that are super easy. So the whole numbers that we got out of this, when we divided it, were 2x plus 5. Well, those are easy integrals. There's no fractions involved. The integral of 2x is x squared. The integral of 5 is 5x. And then we're back to just a regular problem, except this regular problem, the second curveball I threw you was, oh, when it factored to the same thing twice. Did I give you enough time to see that that doesn't work if you just kind of do what you always did? Are you convinced of that?
Yeah, I don't, that's where my question was. I don't see how that doesn't work out where we can't multiply the x minus 2 on the top and bottom on the left side.
You could, but notice you already have a common denominator. Before we did that because we didn't have a common denominator. So we already have one, which means we can add them right now. If you multiply the top and the bottom by x minus 2 and x minus 2 and just make it more complicated, it's still not going to work. Like, test that out. All you're doing is just making it harder for yourself. It's kind of like saying I have, 3/4 and I have 1/4. And even though I can add them right now, I think I'll just multiply the top and the bottom by 4. So now I have 12/16. And this one top and bottom by 4. Now I have 4/16. I get 16/16. Yeah, it's the same answer I would have got if I just added it from the start. It's 4/4. It doesn't accomplish anything. So if you try to do that here, you're still going to get, it doesn't work. There's no x's, unfortunately, in this statement when I add these two numerators together. So how am I supposed to get a 6x if there's no x's? So play with that a little more. So this little trick that some nerd came up with of saying, all right, I'll list the first one as x minus 2 like usual, but the second one I'll list it as squared. That's a way of introducing an x to the problem that makes it work. And so then we actually did need a common denominator. We did have to come back and say, then this one needs another x minus 2 to match the b, which already had 2 of them. Now I genuinely need a common denominator. And so notice that I introduced an x. And so I was able to split this fraction. I was able to split this problem. And this is kind of the big takeaway here. I was able to rewrite that, but it was a much more complicated fraction. It wasn't just 6 over a line, x minus 2, and 7 over some other line, x minus 5. I was able to split it into 2 parts. And then we love minus signs. Now I can do them separately. 6 over x minus 2, super easy. 6 natural log. 7 over x squared, it's also easy, but it's just not natural log anymore. Pretty tricky. So you're going to need to relook at those notes. I need to let you guys go, but you're going to need to relook at those, I'm sure. The assignment's got some trickier questions down near the bottom that make you know that. Okay, get yourself out of here. Stay after if you want to process this a little more. As usual, I'm not going anywhere right away. So.
I was wondering if we could go over a question on the quiz.
Sure.
I was having trouble with number 7.
So obviously I want to strike a balance between sort of doing it for you and giving you some hints. So let me take a look at it and see how I'm going to do that. So what did you try?
Yeah, so I saw that it looked like the Pythagorean theorem.